Hello, and welcome to this GCSE Physics exam preparation video. We're going to be looking at the topic energy stores and transfers, and we're going to revise through that topic. Energy can be thought of as being held in stores. There are different types of energy store, and the energy can be transferred from one store to another. These are the stores that you need to know about. Kinetic energy store. This is the energy stored in a moving object. Gravitational potential energy store. This is the energy stored in an object in a gravitational field. Elastic potential energy store. This is the energy stored in an object that has been stretched or compressed. Thermal energy store. This is the energy stored in a hot object. All objects have thermal energy, even if you think that they are cold. Chemical energy store. The energy stored in the bonds of chemicals. This is energy that is transferred when these bonds are broken or formed. Magnetic energy store, energy stored between repelling or attracting magnetic poles. The electrostatic energy store, the energy stored between attracting or repelling charges. And the nuclear energy store, this is the energy stored in the nucleus of an atom. When energy is transferred from one store to another, there is a mechanism in the model for this to happen. Energy can be transferred in the following ways. Mechanically. This transfer involves forces, for example, pushes and pulls. Electrically, this transfer is when charges move due to a potential difference, for example, current in a circuit. Heating, hotter objects transfer energy to colder ones. And radiation, light or sound waves transfer energy in this manner. So each time energy moves from one store to another, it does so via one of these four pathways. For example, a toy rolling down a ramp. In this example, energy is transferring from a gravitational potential store into a kinetic store. Assuming that there's no friction, none of the energy will go into the thermal store. This happens due to gravity, which is a force, so the transfer is a mechanical pathway. The transfer of energy can get complicated, so to keep it manageable, we use systems. A system is a single object or a group of objects that we are interested in. For example, a ball falling, or an electric motor in a lift moving upwards, or a child on a trampoline. A closed system is a system where it is considered that no matter or energy can enter or leave that system. In our previous examples, the systems were in the pendulum, the string and the pendulum bob are a system, and in the toy car, the car and the ramp are considered to be a system. And that's the end of this video. Thank you so much for listening. Energy changes in a ball being thrown upwards. In this case, the system is the ball. The energy moves from the kinetic store into the gravitational potential energy store because it is gaining height. This is a mechanical transfer of energy as the transfer is due to the forces acting on the ball. As it continues to move upwards, the ball slows down and its kinetic store decreases, but the energy has to be accounted for. The energy moves into the ball's gravitational potential energy store as it gains height. The initial energy comes from the chemical store of the person, and their chemical store decreases, but that's not part of this system. This is about the energy changes in a moving car colliding with a stationary object. The system, in this case, is the car and the wall. In a collision between a car and a stationary object, the energy transfer is from kinetic energy of the car to the thermal energy stores and the elastic potential stores of both the car and the object. This is a mechanical transfer due to the forces acting between the car and the object. During the collision, the car slows down and the amount of energy in the car's kinetic store decreases. Some of the energy goes into the elastic store of the car as the metal is deformed. The metal also heats up, so its thermal store increases. The same happens to the object, the wall. It is deformed, so its elastic store increases, and it heats up, so its thermal store increases. An example of an object being accelerated by a constant force is a ball being dropped from a height. The ball is accelerated by the force of gravity, and in this case the system is the ball. Energy is transferred from the gravitational potential store into the kinetic store. As the ball falls, it loses height and so loses energy from the gravitational potential store. But as it falls, the ball is being accelerated and so is getting faster. This increases the energy in the ball's kinetic store. As this energy transfer is due to the effects of gravity, which is a force, the transfer is mechanical. In this example, a vehicle slows down to a stop. The system is the car brakes and wheels. A vehicle slows down due to the force of friction acting between the wheels and the brakes of the car. As a force is involved, this is a mechanical transfer. As the brakes are applied, the car's wheels slow down. This decreases their kinetic energy store. As this happens, the brakes are heating up, so their thermal store is increasing. Some of the heat goes to the surroundings, which increases the thermal store of the surroundings as well. In this example, we are bringing water to the boil in an electric kettle, and the system is the heating element and the water. The energy is initially transferred to the kettle's heating element electrically, and we could go back to the energy transfers during the generation of the electricity, but that would be very complicated. Instead, let's concentrate on the system containing the water and the heating element. The heating element has a thermal store which is decreasing as the energy is transferred by heating into the thermal store of the water. In many of the questions on energy, you will have to either calculate the energy or use the amount of energy in a store to calculate a missing value. The main equations that you will need to solve these are kinetic energy equals 0.5 times mass times the velocity squared, or EK equals a half mv squared. Gravitational potential energy equals mass times gravitational field strength times the height, or EP equals mgh. And then elastic energy equals 0.5 times the spring constant times the extension squared, or EE equals a half KE squared. The equations in an orange box you will have to learn for the exam. If it's not in an orange box, so the elastic energy equation, for example, you don't have to learn them. They will be given to you in the exam. The law of conservation of energy is one of the most important in physics. It is that energy cannot be created or destroyed. It can only be transferred from one store to another store. This means that the total amount of energy that a system has at the start of a process has to be the same as the amount of energy at the end of that process. There cannot be more and there cannot be less. For example, a ball falling. At the start, it only has gravitational potential energy and the amount can be calculated. Assuming that there's no air resistance in our system, the gravitational potential energy is transferred to the kinetic store. The calculation is as follows. To get the gravitational potential energy, you need EP equals mgh. The mass is 0.053 times by 9.8, which is the gravitational field strength, times by 1.5, which was the height of the ball above the ground. So you know at the beginning of this process, the gravitational potential energy of the ball is 0.82 joules. Because of conservation of energy, then that must be the amount of kinetic energy at the end of the fall. Then you need to use the equation for kinetic energy, which is EK equals a half mv squared. Substitute in the numbers, so you know the amount of kinetic energy because you've calculated it from the potential energy. So that's 0.82, and that equals 0.5 times 0.056, which is the mass of our object, times the velocity squared. This is our unknown. We then need to rearrange our equation so that it equals the velocity squared. So that would be 0.82 divided by 0.5 times 0.056. And notice that that's in brackets, so the calculator does the correct calculation. And that gives us an answer of 28.29, but that's the velocity squared and not the velocity. So then we have to square root that, and that gives us our final answer of 5.31 metres per second. This is a second way of doing the same calculation, but this time we're going to do it without using mass. As we've said, we're going to assume that there's no air resistance in our system, which means that all the gravitational potential energy is transferred into the kinetic store. This being true, we can say that the potential energy, the gravitational potential energy, equals the kinetic energy. So we can use this to get a new expression, and our new expression is mgh equals a half mv squared. As we have mass on both sides of the equation, we can cancel those out, and that leaves us with GH equals a half v squared. Now we can substitute in our numbers and rearrange, and we end up with v squared equals 9.8, which is our gravitational field strength, times 1.5, which is our height, and we divide that by 0.5, which is our half from the previous equation. And this gives us 28.29. This is v squared and not v, so we need to do the square root of this. So the square root of 28.29 gives us v, which is 5.31 metres per second. This method can be useful if you are doing a question that hasn't actually given you the mass. You're using the principle of conservation of energy to work out your final answer. Power questions come up in every Paper 1 exam. Power is the rate of doing work or the rate of energy transfer, and this is because work done equals energy transferred. To put it more simply, power is the amount of energy transferred from one store to another every second. We have two equations here for working out power. Power equals work done divided by time, and power equals the energy transferred divided by time. You'll have to learn both of these equations for the exam. And also don't forget your units. Power is in watts, work done and energy, because they are equivalent to one another, they are both in joules, and time is in seconds. You may also need to do a conversion to get your units into the correct standard form for these questions, and 1 kilowatt is 1000 watts. So for example, 3 kilowatts is 3000 watts. 1 minute is 60 seconds. So for example, 20 minutes is 1200 seconds. Two lifts are exactly the same except for the power of their motors. Lift A has a motor of power 15 kilowatts and lift B has a motor of power 12 kilowatts. They carry the same mass, 1250 kilograms, and they carry that mass the same distance, 14 metres. What is the difference in time taken? First, we have to work out the work done by the lift. As work done is the same as energy transferred, we can use the equation for gravitational potential energy. So for lift A, gravitational potential energy, EP, equals mgh. Substitute in the numbers, and that gives you EP equals 1250 times 9.8 times 14, and that gives us an answer of 171,500 joules. If we do the same with lift B, we find that we get the same answer because the inputs were the same. We had the same mass, the same gravitational field strength, and the same height. We can now use the power equation to work out the time taken for each lift. Power equals work done over time, but for the power, we need our power rating to be in watts, not in kilowatts. So to convert from kilowatts to watts, we need to times by 1000. So 15 times 1000 gives us 15,000 watts. Substitute that into the equation, gives us 15,000 equals 171,500 divided by T. Rearrange that for T, calculate your answer, and that gives us 11.4 seconds. For lift B, we do the same thing. We need to convert kilowatts into watts, so 12 times 1,000 gives us 12,000 watts. Substitute this into the equation, 12,000 equals 171,500 divided by T. Rearrange, calculate, and our time is 14.3 seconds. Now the question asked us for the difference in time, so we now have to calculate that. So 14.3 minus 11.4 gives us a final answer of 2.9 seconds. And that's the end of Energy Stores and Transfers Part 1. See you in Part 2.